Welcome to section 6.3. In this section, we're going to continue our investigation of trigonometric equations. They call this trigonometric equations 2. And so they're going to expand our experience a little bit. And what you're going to know in each one of these is it's not just going to be sine of x or cosine of x. Oftentimes it's like this first one where it's a 4x involved. And so my suggestion to you is totally take a look at how they're explaining to do it in the book. Because what you want are just some different approaches, and then you'll find one that resonates with you. So please don't just rely upon this video. See what they're doing in the book as well, and see if that works better for you. So as we look at this tangent of 4x equals 0, one perspective could be, oh shoot, I got to use the double angle formula and get that down to tan x. I think that's going to be quite messy and not helpful at all. We shouldn't be daunted by these 4x's at all. Because they're actually easy to deal with. So I want you to remember about what 4x does. What's this 4 do? And so let me come and get a pen out. What's this 4 right here really do? Remember, it adjusts the period. So our new period, it was pi for tangent, and now it's pi over 4. So that means it's going to repeat itself every pi over 4 instead of every pi. And so what that means is, now this is an x, so x corresponds to radians. So that means in 0 to 2 pi, instead of having the 2 answers that we were going to look at, it's going to have 4 times those answers, or 8 answers. Let me just restate that. We took our period and that 4 takes that period and makes it 4 times as small, meaning it can repeat itself 4 times in 0 to 2 pi. And so therefore we're going to get 4 times the number of answers out of that. Well, actually, let me restate that. It's going to repeat itself 4 times in every period, which is just pi. And so we're going to get 4 times the number of solutions between 0 and 2 pi. We are going to get 8 solutions out of this thing. So it's nice to know what you expect. So here's my suggestion about how to do it. And again, just because I'm the one suggesting it doesn't mean it's the best method out here. It's just the one I was going to say I'm used to, but it's the one I grew up with. So here's what I would suggest to do. And I'll try to make it as trackable as possible. I would suggest that you come in here and put a u. Just solve this equation. Tangent of u is equal to 0. Well, we could do that. That means u would be equal to, well, let's think about the times tangent is 0. It's 0 at 0. It's also 0 again at pi. And what we want to do, those are the only 2 solutions it has between 0 and 2 pi. Because it's not including the 2 pi, but we're going to remember that we're expecting 4 times the amount of solutions. We're going to go out 4 times. So here's 1 time through it. Then there's the 2 pi and the 3 pi. There's the second time through it. Then there's the 4 pi and the 5 pi. And then there's the 6 pi and the 7 pi. We just know we're going to get 4 times the answers. Now, we didn't have u. In fact, it probably would have been better if I put this as a red u. We know what u is. U is 4x. So 4x is equal to all these. Well, they didn't ask me what 4x was. They asked me what x was. So guess what I have to do? I got to take everybody and divide it by 4. 0 divided by 4, 0. Pi over 4. Pi over 2. 3 pi over 4. Now notice all of these answers are between 0 and 2 pi, and every single one of them will work. And then 4 pi divided by 4 pi. 5 pi over 4. 6 pi over 4, which we often call 3 pi over 2, and 7 pi over 4. Now look how close I am to 2 pi, which is 8 pi over 4. I'm not going to go out that far because 8 pi over 4 is exactly 2 pi, which isn't included in my desired interval. It goes from 0 to 2 pi, but doesn't include the 2 pi. So again, what was the process? To realize that we had a 4x, not to be daunted by that. To just treat it like it was just a letter. Realize that we're going to get 4 times as many of solutions. So here's the 2 that came out between 0 and 2 pi. So we go out 3 additional times for a total of 4. And then why are we doing that? Because we're going to bring everybody back by a factor of 4. And we're going to end up inside 2 pi. All of these values are between 0 and 2 pi in our answers. And those are the 8 answers that will be reflected in the back of the book. If you give me only 6 of them, partial credit, right? If you give me 2 of them and only 2 of them, probably no credit. It just meant that you weren't paying attention to what you had. So notice that there's 4 times as many answers in there. So this is my method. It's almost like casting a big wide net and then bringing everybody back. Again, please take a look at what the book's going to suggest to do. So I'm going to erase this, otherwise we're going to run into some issues solving this next one with space. So take a look at the next one while I'm erasing this. It's cosine of 2x minus cosine x is equal to 0. Now here I should think to myself, I got a problem. And the problem that I have is that I got things in 2x's and x's, and that's just not going to work. You can't factor that 2 out. This isn't cosine times 2x. This is cosine of 2x. So what can we do? We can use one of our identities. Now, I would suggest using one that just has cosines in it. Don't introduce a sign. That's going to complicate things. Remember, there were multiple forms of cosine 2x. And the best one I think to use would be the 2 cosine squared x minus 1 representation. So I just replaced that with 2 cosine squared x minus 1. Minus cosine x is equal to 0. Why was that so advantageous? Because now I can rearrange a little bit and realize I have a polynomial in cosine. That's why a good Algebra 2 class, a good intermediate algebra class would have had you solve things that were quadratic in form. Is because if they didn't do that, they did you a disservice if they thought they were helping you by not covering that. But this is definitely quadratic in form. A number, cosine, and the cosine squared. So we know how to factor this. This is 2 times, whoops, no squared, sorry. This is 2 cosine x. And a cosine x in the next one. A 1 and a 1 for sure. It's a negative here and a positive here so that we can get our 2 out in the middle and we're set. If you just track that through FOIL, you'll get your 2 cosine squared. You'll get a negative 2 cosine x plus cosine x for negative x, and you'll get a negative 1. So you know what that means. That means one of the solutions sets comes from cosine of x equaling negative 1/2. And the other one comes from cosine x equaling 1, because those are the 2 ways those 2 things would be equal to 0. So now we just have to think, well, when is cosine x equal to negative 1/2? Well, let me think about when it's equal to 1/2. That's at a pi over 3 angle. So I need the pi over 3 angles where cosine is negative. Well, that's the second quadrant at 2 pi over 3, and the third quadrant at 4 pi over 3. There's the 2 solutions from that first one. Cosine x equaling 1. That definitely happens at 0. And where else? It would happen again at 2 pi, but 2 pi is not included. So we shouldn't include that. So again, 2 pi is not included for my x's that are there. And if those were thetas, we would do them in terms of degrees. Let's see if that happens down here. Nope, everything's x's. So that's good. I prefer working in radians. I can think better in radians. So here's an example. Let's remind ourselves what's happening with this 2. This 2 is giving us, making our period that was 2, sorry, Let me write that differently. We're taking our period that was 2 pi and dividing it by 1/2, and so we're going to get a 4 pi period. It's actually elongating it. We're going to get less solutions. We're going to get half the amount of solutions. So we're expecting half the solutions. So if we go and compare, the 4 told us we were going to get 4 times the amount of solutions. The 2, the 1/2 I should say, is telling us we're going to get half the solutions. It does work that way. So now we know what to expect, so let's go solve. So we got sine squared. X over 2 is equal to 2. Take the square root of both sides. That means sine of x over 2 would be equal to two things. Either root 2 or sine x over 2 is equal to negative root 2. We should respect them both. If we don't, then we're going to have some issues. Okay, well, think about for a moment what the square root of 2 is. The square root of 2 is 1 point something. Well, that's a problem. Sine has a maximum value of 1 and a minimum value of negative 1. Well, that means this has no solution, and this has no solution. Let me erase that and make that look a little bit better. Neither one of them have any solutions coming out. There's no solution because root 2 is greater than 1. They want to make sure that you're thinking. I'll try to structure these where you do not have to go to a calculator in order to get your answers, and that's why they'll most likely be in radian form. Okay, on your exam. Let's look at this last one that's on this page. Sine x cosine x is equal to 1/4. We're going to have to do something creative here because I can't say it's not equal to 0, so I can't say either sine x is 0 or cosine x is 0. It's inappropriate to say either sine x is 1/4 or cosine x is 1/4. That's absolutely positively wrong. There are two other numbers that you can multiply together to get 1/4 other than 1/4 and 1. So that's weird. We can only do that if it's a 0. So we got to think creatively. I can't switch out sine for cosine because it's not sine squared, and similarly, I can't switch out cosine for sine. So what could I do? I could start to think about all the identities that we have. There's one that I could create. I'll come in here in red. If I put a 2 out in front of there, that's an identity. And if I put a 2 on that side, I got to put a 2 on this side. Otherwise, I'm not balanced in my solutions. Now, do you remember who 2 sine x cosine x is? You'll come to that exam having that sheet with you, so think this way. If you're saying to yourself, I wouldn't have known to do that, well, that's why you're getting instruction and having opportunities to practice with it in the homework. Nobody expects instant understanding and recognition. 2 sine x cosine x is obviously sine 2x is equal to 1/2. So this turns into really what we had for the first problem, number 16, the tangent of 4x. We're expecting double the solutions. And so we're going to go twice the distance out. So I'm going to look at this, and I'll continue to do my u substitution because I find more people can follow that. So I'm going to let u be equal to 2x. And then we're going to consider then sine, and I'll keep the red in there for emphasis, sine of, sine of u. Okay, so sine of u is equal to 1/2. Perfect. When is sine equal to 1/2? Well, you know that that's at pi over 6, also in the second quadrant of 5 pi over 6. Then you have to go 2 pi later for each one of those. So pi over 6 plus 2 pi, or pi over 6 plus 12 pi over 6 is 13 pi over 6. And 5 pi over 6 plus 2 pi, which is 12 pi over 6, is 17 pi over 6. So the first two that are listed are the only ones that are between 0 and 2 pi. Now, why am I going to get these other ones? Because I know I'm expecting double the solution. And so what do I know? I know that 2x it needs to be equal to these. So what's the x's that I'm looking for? Divide everybody by 2. Pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Those are the angles who, if I were to plug them into the original, would yield 1/4. And they're all between 0 and 2 pi. And there's no other ones. If there were other ones, I would have been able to capture them. If I go one more out and add 4 pi to this, if I had another 12 pi over 6 to what I had with the 13 pi over 6, I'm going to get farther out. I'm going to have 25 pi over 6, which would be 25 pi over 12. And you can see that happen. Again, this is my way of doing it, to respect the fact that the 2 shrinks the sine graph to complete in half the time, so therefore I get double the solutions out from 0 to 2 pi. It's a great thinking exercise. So this might turn out to be a longer video, but I'd like to just finish here and do these problems as well. So for example 2, they're grabbing from questions that are in the late 30s. Solve equation x in radians, theta in degrees for all exact values. Notice that we want exact value. Homework says to round. Obtain that exact answer first, because this will be your exam answer, and then round that so that you can get your homework answer using the least possible non-negative angle measures. So what do you notice as you read through all that? What you should notice is that they didn't limit where our answers could be. We have to give them all exact values. It could be easy to overlook that all statement right there, but they need every single answer. So that's where we're going to be doing the n pi's, 2 n pi's, whatever is needed. So what do? Let's watch it happen here. So here we have sine 2x equals 2 cosine squared x. Okay, so let's replace sine 2x. The only thing that we can replace it with is 2 sine x cosine x. And that's going to be equal to 2 cosine squared x. That's not a bad position to be in. Let's bring that 2 cosine squared x over. So that's 2 sine x cosine x minus 2 cosine squared x is equal to 0. You know why we're doing that, so that we can factor. Pull out the 2, pull out the common cosine, and be left with sine x minus cosine x. Okay. As we go through there, and that's equal to 0. Well, let's start solving this one. We need 2 cosine x to be equal to 0, which would mean cosine x would be equal to 0. And we can think of where that happens. That happens at pi over 2, and it also happens at 3 pi over 2. So it's happening every n pi. There's part of our solution. That will give every single number there. So it's happening at pi over 2 and at 3 pi over 2, and so they're just a distance of pi always apart from one another. So that's why we can get by with adding n pi and not producing the second one. Now this next one is great. And you could get a little bit confused, like, I don't know how to do that. Well, let's see what it means. If you have sine x minus cosine x equaling 0, it means that sine x equals cosine x, that they're the same sign and also the same value. Well, where are sine and cosine both the same sign? Obviously quadrant 1, but also quadrant 3. They're both negative there. And you know where they are both the same. They're both the same at only one angle, a pi over 4 angle. So pi over 4 plus 2n pi would absolutely give us all those first quadrant angles where sine and cosine are both root 2 over 2 and the same. And the other place that happens is in the third quadrant plus 2n pi. So that first and third quadrant plus 2n pi. Right? So one's here and the other's here. So if we look at that really carefully, maybe there is a better way to do that, because it does look like they're pi apart. So this is too much. So you want to take a look, and whenever they're straight across from one another, you can make it more simple. So because they wanted it where they were both equal, that happens in the first and third. we can get by with just 1. So we're going to erase this 5 pi over 4. We're going to erase the 2. And it's just happening every n pi. That'll do it for us. So that is what they mean by the least possible non-negative angle measures. Done. Those two right there would produce every time that equation is solved. Okay. Let's go look at this other one over here. Cosine x is equal to sine squared of x over 2. Need to be a little bit creative here. So what about sine squared of x over 2? Well, remember your half angle formulas, right? Let's remind yourself of it. What's the sine in particular? Do you remember what the sine of x over 2 is? Because what we have is the sine of x over 2 squared. Well, let's go remind ourselves what that is, and we're going to realize really quick that they're trying to be helpful to us. Now, it is this. The sine of x over 2 is equal to plus or minus the square root of 1 minus cosine x all over 2. And we're supposed to square that. So it wouldn't matter whether it's positive or negative. It would square to be positive. The square root would go away, and we would just be left with 1 minus cosine x all over 2. So here's what we have. We have cosine x is equal to 1 minus cosine x all over 2. That means 2 cosine x is equal to 1 minus cosine x. Or 3 cosine x is equal to 1. Or we need to figure out where cosine x is equal to 1/3. Now you and I don't know where cosine x is equal to 1/3. Now remember, x is in radians. So make sure your calculator is in radian mode. If you put a degree, I'll give you some credit, but certainly not full credit. So we're going to put our calculator in radian mode. Let me do that really quick, because it was in degree. And I'm going to do the cosine inverse of 1 divided by 3. And it's going to tell me that the answer is 1.23. It's 1.230. So I'm going to just say x is equal to 1.23 radians plus 2n pi. So where is that? That's this first quadrant. We also need a fourth quadrant angle. So I need to take and back myself off of 2 pi by 1.23. So I'm going to type into my calculator 2 pi. So this one right here is the 1.23. This one right here is, I apologize, this one right here, right? Because we need it non-negative. So let me go in there and erase that. This one down here, that's 1.23 degrees off, is 2 pi minus 1.23, or 5.05. Now look at the picture of your solutions. They're not right across from each other. You can't make it any different than that. They're two unique answers that don't loop together in a consistent fashion. So that's what we have. We have those answers right there that would be reflected in the book. So this is number 36. I could give you that on the exam because you're not doing it in class. If you're in class, I'd have no calculators and keep everything in the memorizations, but I can't do that. So here we go. What are we going to do here for number 38? Well, let's see. Cosine 2x. So this is 4 cosine 2x is equal to, what if we looked at it like this? 4 times 2 sine x cosine x. Now why would I do that? That'd be 4 cosine 2x is equal to 4 sine 2x. I remembered that from before, so just a little trick to come through. It wouldn't do me any good to subtract the 8 over, because factoring out, I'm going to have two different functions of cosine, which is going to be problematic. So right now I've matched them in terms of 2x's. Now, if we divide both sides by 4, we get cosine 2x then would need to be equal to sine 2x. Here's what I would suggest. I would suggest dividing both sides by cosine 2x. Now, why would I do that? I get a 1 over here. And what's sine divided by cosine? Tangent 2x. And let me reverse this a little bit and come back in here. Tangent of 2x. You know all about where tangents equal to 1. And we're going to have double the amount of solutions. Tangents equal to 1 at pi over 4, at 5. Oh, it is saying, I didn't catch that at first, because it is saying to solve it between 0 and 2 pi. That's nice. So 5 pi over 4, those are the two that are in the first wave, but we need to go out to a second wave because we're getting double the answers. So I got to add 2 pi, right? But 2 pi really is 8 pi over 4, so I get a 9 pi over 4. And if it was a 5 pi over 4 plus 8, I'd have 13 pi over 4. That's how I'm finding those. That's what 2x would have to be equal to. So at some point, you'll be really good with not having to show the u, but just know that you're extending your answers. So let's all bring them back in. So that means one of the answers is pi over 8, 5 pi over 8, 9 pi over 8, and 13 pi over 8. And those are our 4 answers, all between 0 and 2 pi. If we were to go out one more time, we'd have extended beyond what the 2 could help us bring back. Awesome. And then the last one that's an example from this section. So here I'm expecting half the solutions. Here I think I will do a u substitution so that I don't have to keep writing all those out. So I'm going to let u, let me not use that. Let me do it this way. I'm going to let u be equal to x over 2. And so doing that, let me rewrite what we have. Maybe I'll write the whole thing in red. Sorry about that. We'll do sine u plus cosine u is equal to 1. That's a helper equation in order for me to solve this. So what in the world would we do here? Well, there's a trick, as there sometimes are. So there's not much that you can do. We don't have a straight substitute out for sine to cosine because it only works with this squared. So one option is to isolate one of them and then square both sides. Ooh, I have a mistake in there. Did you see it? I should have brought it over through subtraction. And so we're going to square both sides. And here's what I get. I get sine squared u is equal to 1 minus 2 cosine u plus cosine squared u. And you're wondering, well, how did that help me? And again, I could have, or why did you decide to move cosine over? I could have moved sine over and it would work just the same way. We would just get the answers a little bit differently. Now, our goal was to get everything in terms of the same trig function. Now I can. So at first I was stuck because there's no straight thing from sine to cosine. Here I wasn't as stuck because I could divide both sides. There was only just 2 terms. It's the 3 terms that's hurting me here. And so I did a trick. I squared both sides. Remember to do FOIL on the right hand side. Then we know what this is. The sine squared u is 1 minus cosine squared u. Oops, 2 cosine u plus cosine squared u. And so if I bring everything to one side, I get 0 is equal to, my 1's go away, so negative 2 cosine u plus 2 cosine squared u. So that means I can factor out, I could factor out a 2 and a cosine u. If I do that, I end up with negative 1 plus cosine u. Not wanting to do too much. Personally, I would have flipped that around to cosine u minus 1, but this works just fine. That means part of our solutions come from when cosine u, let me put the 2 cosine u so you don't wonder where that went, equals 0. And the other one comes from negative 1 plus cosine u is equal to 0. So if I go back to the first one, that's when cosine u is equal to 0. And if I solve for cosine u here, it's equal to 1. Awesome. Well, remember what u was. U was x over 2, right? So I'm wanting to solve the equation. Let me go back to black, right? Now we'll go back to the original. That means I need cosine of x over 2 to be equal to 0, or cosine of x over 2 to be equal to 1. And we're going to get half the solutions now because of that 1/2 that's in there. But let's think for a minute. Where is cosine 0? It's 0 at 0. And, no, it's not 0 at 0. Apologize. It's 0 at pi over 2 and at 3 pi over 2. Okay. Now, I'm listing both of the solutions out that happen within the first interval. I don't need to go to a second one because I'm not doubling my answers. I'm actually taking half. I just want you to see that the 3 pi over 2 is a waste of time because you knew you were going to get half the original solutions. But we'll see that. Here, where is it equal to 1? X over 2 would be equal to 1 just at one place, at 0. Right? Because then it goes, if I think about cosine, it's at 1, then it goes to 0, then negative 1, then 0, and then back to 1 at 2 pi. But 2 pi isn't included in my solution set, so I wouldn't even include that as part of the original. Now let's double everything. So we need to solve this thing for x, so we're going to double things, and we're going to get pi, and we're going to get 3 pi. But 3 pi has to be thrown out because it's beyond 2 pi. But we're not shocked about that because we're expecting half the answers. And then if I double 0, I get 0. So the two answers for x are just simply 0 and pi. That's going to finish that one out. So have fun with this. It does require time and patience, but it's going to build a better you in terms of algebra manipulation and solving equations, which we need for future classes.